So let's dig into optimization and linear programming so you can actually get a sense of what these problems look like when we sketch them out. So we all face decisions about how to use limited resources. And in fact, healthcare is a perfect example of this. Who do we vaccinate first with COVID? Who do we prioritize for ventilators? What happens when there's a hospital-wide shortage of a certain medication? And we need to consider what limited resources to budget in your day-to-day life. For example, the emergency department at Ruby Memorial in Morgantown had a hospital-wide shortage of Dilaudid. So when treating patients with pain complaints, they had to get creative about using other medications and trying to calculate equivalencies for medications like Dilaudid and morphine. The field of management science that finds the optimal or most efficient way of utilizing limited resources to achieve the objectives of an individual or business. That's what our aim is with mathematical programming. So it's management science, and we're trying to just do the best with what we have. You might be kind of familiar with this concept just with the word optimization. So what does optimization mean in practice? Well, it can mean determining product mix. So what medication should we give a complex patient in the ICU? Manufacturing. So once that vaccine is developed, how do we manufacture it to route it and logistically handle it and get it to patients who need it, as well as financial planning, which is critical in any business organization. And I challenge you now to take a moment to think about examples from your life, school, or work where optimization is exceptionally important to you, or to the scenario that you find yourself working in. So the characteristics of optimization problems should look a little bit familiar. Our decision variables are indicated with the letter X. So these are the variables that we believe influence Y, or our objective cell. Constraints are limitations on variables. So those decision variables are not necessarily going to be infinite. There may only be a range. For example, with medication, there may only be a certain therapeutic range. So one of our X's may be that medication with a limited therapeutic range, and its constraint is the limitations of its therapeutic range. And you might notice that when you look at the dosages in which medications come in. They don't come in all kinds of infinite dosages, because not all dosages are therapeutic. And our objective is to maximize or minimize some function of variable, which is generally expressed with the letter Y. So mathematically, and again, we can always go back to using words based on the prior presentation, but what we're trying to do is we're trying to maximize or minimize a function of our decision variables, and that's subject to some variables being less than or equal to B, others being greater than or equal to B, and others still being equal to B. And B is that value that indicates the constraint on that X variable. And just to point it out, because we will be working with both linear and nonlinear variables, if all functions in an optimization problem are linear, the problem is a linear programming problem. If they're not linear, we have a nonlinear programming problem, and we have ways to handle that too, and we'll get there. So, simply put, linear programming problems are structured like this, where we're looking to maximize or minimize our decision variables subject to their constraints. So let's walk through an example that has absolutely nothing to do with medicine. Well, I don't know. If you have back pain, maybe hot tubs do feel like medicine. So Blue Ridge Hot Tubs produces two types of hot tubs, aquaspas and hydroluxes. And each of these models has different decision variables. They all require pumps, labor, tubing, and unit profit, so those are our decision variables. But then the specific values of them differ. So the aquaspa requires 9 hours of labor, while the hydrolux requires 6 hours of labor. The aquaspa has a unit profit of $350 per unit, while the hydrolux has a profit of $300 per unit. We have 200 pumps, 1,566 hours of labor, and 2,880 feet of tubing available. So these are our constraints. So our table lists out our decision variables, and then beneath that are the constraints that we have. And there are 5 steps in formulating linear programming models. First, we need to understand the problem. Next, we need to identify the decision variables. In this case, our decision variables are x1, the number of aquaspas to produce, and x2, the number of hydroluxes to produce. So then to state the objective function as a linear combination of our decision variables, we're trying to maximize 350 times x1 plus 300 times x2. And then we need to state our constraints as linear combinations of the decision variables. So each model requires one pump, so 1 times x1 plus 1 times x2 must be less than or equal than 200. So we cannot have any more than 200 pumps. And the same applies for labor and tubing. We also cannot produce a negative number of hot tubs, so number 5 identifies any upper or lower bounds on the decision variables, and that is that x1 must be greater than or equal to 0, and x2 must be greater than or equal to 0 as well. So this is what our equation looks like. And again, you don't see a lot of words, but if you're getting kind of confused, you can change x1 to say aquaspa. ST means subject to, so those are our constraints and our limitations. And max means to maximize it. But again, if the letters get too confusing for you, you want to submit your work in mathematical format, but go back to using words. It might make a huge difference. So there are a few approaches that we can use to try to solve linear programming problems. First is intuitively. So each aquaspa generates the highest unit profit, $350. So let's make as many of them as possible. So how many might that be? Well, x2 is going to be equal to 0 because we're not producing any hydroluxes. So our first constraint is that 1x must be less than or equal to 200. Our second constraint is that 9 times x1 must be equal to or less than 1566. And the third constraint is that 12 times x1 must be less than or equal to 2,880. Or if we break it down by, if we reduce the equation, you'll see x1 is less than or equal to 174, or x1 is less than or equal to 240. That's just from dividing 1566 by 9 and dividing 2880 by 12. If x2 is equal to 0, the maximum value of x1 is 174, and the total profit is 350 times 174 plus 300 times 0, so $60,900. Is this solution feasible? Is it optimal? Well, we're not using all of the resources available to us. Look at the second constraint. The maximum number of X1 or aquaspas we can produce is 174. So we could be leaving some things on the table because the aquaspa requires more labor, and therefore, who knows, if we didn't have that constraint or we were considering the second, the Hydrolux, we may find that we could actually produce more tubs and generate more profit. But intuitively, this is one solution that could be found. We can also solve these problems graphically when we only have two values for x, and in this case we do. We have our aquaspa and our Hydrolux. The constraints of a linear programming problem defines its feasible region, and we're going to take a look at that in just a second. The best point in the feasible region is the optimal solution to the problem. For LP problems with two variables, it is easy to plot the feasible region and find the optimal solution. So here we want to plot our very first constraint, and that's the boundary line of the pump constraint. So we have x1 on the x-axis and x2 on the y-axis. x1 is our aquaspa and x2 is our Hydrolux. And our first constraint we're placing on this chart is the boundary line of the pump constraint. So we see that for x2 we're at 0, 200, so that would be 200 pumps for the Hydrolux. And then on the x-axis we're looking at a scenario where we might have 200 pumps for the aquaspa. And anywhere that is shaded in blue is a feasible constraint. It is a solution that we could make work for our scenario. But we have additional constraints that we need to consider as well. So now we're adding the boundary line of the labor constraint, and there are different amounts of labor required for the two different types of hot tubs. So what we find is that for our Hydrolux, the axis, the line intersects well above the line for the pumps. However, the labor constraint intersects 0 at 174, which gives us that limitation of 174 hot tubs. Meanwhile, with the Hydrolux, if we had 261 pumps, we could make 261 hot tubs with this constraint. What we're seeing is that our feasible area is getting smaller and smaller. Let's add that third constraint of the tubing. The tubing cuts off a little bit more of the feasible region for the Hydrolux, but not so much for the aquaspa, but it still has an effect on that feasible region. And there are several ways in which we can go about trying to find the feasible region when we can sketch out our models. So one is plotting a level curve of the objective functions. So you draw a level curve and you work your way out until you reach the optimum point. So here is our first curve where we're looking at we have one level curve here that is well within the objective function area. We have another level curve that is also well within the objective function. But what about this situation where we have one level curve and it touches one corner? And other than that is not within the objective function area. And that may seem unintuitive, but that is actually our optimal solution. Our optimal solution is where it is at a corner point where we can maximize our objective. So the optimal solution occurs where the pumps and labor constraints intersect. And this occurs where x1 plus x2 is equal to 200 and 9x plus 6x is equal to 1,566. From equation 1, we have x2 is equal to 200 minus x1. Substituting equation 3 for x2 in equation 2, we have 9x1 plus 6 multiplied by 200 minus x1 to equal 1566, which reduces to x1 is equal to 122. So the optimal solution is x1 is equal to 122, x2 is equal to 78, and our total profit is 66,100. This makes you nervous or panic. Don't do that yet, because you're going to learn how to do this using spreadsheets. And when you're in the spreadsheets, it becomes a lot easier to just run the equations and then carefully interpret the results. We can also enumerate corner points, where we look at each and every one of the corner points in along the edges of and within our model to find which one yields the highest value. And we find that production of 122 aqua spas and 78 hydroluxes is still the very best, yielding a profit of $66,100. And you can see the original gut instinct result here as well, where we're producing 174 aqua spas and 0 hydroluxes. This technique doesn't work if the solution is unbounded. Unbounded solutions are those scenarios that don't have solutions. So when we're working on graphical solutions to linear programming problems, we want to plot the boundary line of each constraint, identify the feasible region, and locate the optimal solution by either plotting level curves or enumerating the extreme or corner points. Some of the issues we run into with linear programming models is that there are some scenarios where there are alternative optimal solutions, redundant constraints, unbounded solutions, and infeasibility. And I'll quickly go over those so that you understand what they mean when you encounter them. In this scenario, we have alternate optimal solutions. So everywhere that objective functional level curve is aligned with or lays perfectly on top of that feasible area, those are alternate optimal solutions. And picking just one randomly is not an effective way to solve a problem. We may also have redundant constraints, and redundant constraints are those that have no bearing whatsoever on the feasible region. So here in orange, I have the boundary line of the pump constraint, and it does not touch the feasible region that's given. And therefore, we may not want to include it in the model. It may just increase confusion and lack of clarity. Unbounded solutions are those that you are able to create an area of feasibility. However, the area of feasibility does not align with an optimal solution. And finally, infeasibility is a scenario where the feasibility region or areas do not overlap at all, and there's no way that you can develop an area of feasibility that will work for your model. That is rare, but it is a challenging situation, and instead of giving up, I urge you to go back and reconsider the elements of your model, see if you can make some changes to your constraints, and go from there. I hope you found this very helpful. I can't wait to get you going with this using Excel Solver. If you do not yet have Excel Solver, I strongly recommend getting it set up in your version of Excel. Great talking to everybody, and we'll see you next time.